Now we will discuss pH of strong bases. Example, we have got NaOH. Similar as we have discussed for pH of strong acids, exactly similar things will be here. Example, suppose you have got 10 to power minus 2 molar NaOH solution. NaOH is supposed to be a strong base, strong electrolyte, and a strong electrolyte means it will dissociate completely. So it dissociates completely and we get Na plus plus OH minus. Now the concentration of NaOH given is 10 to power minus 2 molar. It dissociates completely. We get 10 to power minus 2 molar Na plus ion, 10 to power minus 2 molar OH minus ion. Right. Now this, in this case, pH again will be minus log of H plus ion concentration. Two things we can do here. One thing is, instead of pH we directly calculate pOH, and pOH in a similar manner is given as equal to minus log of OH minus ion concentration. Now this will be equal to minus log of 10 to power minus 2, means pOH here comes out to be 2. Now just now we have got one equation that Kw equal to concentration of H plus into OH minus, right? We take minus log on both sides. Minus log of Kw becomes pKw, minus log of H plus becomes pH, and minus log of OH minus becomes pOH. So we get pKw equal to pH plus pOH. At 25 degrees Celsius, again this is going to be 14, Kw will be 10 minus 14, minus log of that becomes 14, equal to pH plus pOH. pOH what we got for NaOH is 2, we substitute it as 2. So we get pH as equal to 14 minus 2 means 12. Right. So pH of a 10 minus 2 molar NaOH solution is going to be 12. Exactly similar manner, like we have got exceptional case of HCl, 10 to minus 8 molar HCl just now we discussed. Similar manner, if you take a highly diluted solution of NaOH, suppose 10 to minus 8 molar NaOH solution we have got. Now if we solve the problem in a similar manner like we have previously solved for 10 to minus 2 molar NaOH solution, how it becomes, how weird it looks. See, this is 10 to minus 8, we substitute here 10 to minus 8, as a result pOH comes out to be 8. Got it? Now if pH is 8, come back here, this here pOH, sorry, if pOH is 8, this becomes 8 here, right? We substitute pH equal to 14 minus 8, and surprisingly pH comes out to be 6. If you remember Sorensen scale, pH scale, below 7 the pH is for acidic solutions. Obviously in listening only it looks ridiculous that we have got an NaOH solution which is acidic. Got it? So again same thing will be done which we did previously with HCl. In this case again here the concentration of OH minus coming from water will have to be discussed. Substitute the value, and here now pH will come out to be slightly greater than 7, 7.1, 7.0, something like that will come out to be pH. Got it? So procedure will remain exactly same, it is not going to change. Next thing which we are going to discuss here is pH of weak acids. Example, we pick up here acetic acid, that's a standard moderately weak acid, not very weak, not very strong, so moderately weak acid. This one we will discuss here. Weak acids are those acids which do not dissociate completely, and an equilibrium is established between them, between the undissociated acid and the dissociated acid. How? See that part. Acetic acid we take, it will establish an equilibrium to give acetate ion and H plus ion. We take one moderately weak acid and we say the concentration of acetic acid here is C. We know one term is used to show how much of the acid is dissociating, and that is called degree of dissociation. We assume here the degree of dissociation of acetic acid is alpha. So this will be C into 1 minus alpha. So concentration of acetate ion in the solution will be C alpha, as well as H plus ions, it will be C alpha. Now, because this is an equilibrium, we'll have some equilibrium constant also. Equilibrium constant for dissociation of acids is known as Ka. It is called as Ka. And Ka for this will be equal to concentration of acetate ion into concentration of H plus ion upon concentration of acetic acid, undissociated one, which has not dissociated at the time of equilibrium establishment. Right, now we substitute the values. This becomes C alpha into C alpha upon C into 1 minus alpha. What did CC get cancelled? So we get it as equal to C alpha square upon 1 minus alpha. Now, one thing you can observe here, that in this type of cases, quadratic equation will be formed, which mostly, otherwise we should say normally, are quite difficult to be solved. And if the question comes in IT exam where you have got approximately, or any exam where you got approximately 1.5 minutes, 2 minutes, or maximum 2.5 minutes to solve the problem, solving quadratic equation becomes a pain. Okay, so here we are going to take some approximations which simplify the equation as well as the calculations. Under what conditions we can take approximations, up to what limit we can take approximations, those things we will learn now. See it carefully. Suppose you are given a certain concentration for acetic acid. I'll tell you one simple approximation which is taken here. This we got as Ka, dissociation constant of acid, equilibrium constant of acid, equal to C alpha square upon 1 minus alpha. What we do in this case, we assume that because acetic acid being a very weak acid, it is not dissociated properly, and its degree of dissociation alpha is negligible as compared to 1. This is one approximation we are taking here to simplify the calculation. Remember, to simplify the calculation, we can take only valid approximations. If you take invalid approximation just in order to simplify the calculation, so your answer will become completely wrong. Okay, so we'll cross check it whether our approximation was valid or not. Okay, see, if I neglect alpha from here, then we get Ka as equal to C alpha square. From here we get alpha square as equal to Ka by C, and alpha becomes equal to square root of Ka by C. Now listen properly. If the value of alpha from here comes out to be equal to or less than 0.1, it comes out to be equal to or less than 0.1, we say our approximation to neglect alpha here as compared to 1 was valid. If the approximation was valid, you should become very happy. What you have to do now, simply take this value of alpha, multiply with C, you will get C alpha. Right? Simply to get pH, what you have got to do is take minus log of C alpha. C alpha is what? Concentration of H plus ion. Simply take minus log of C alpha, you get pH from here. But if the value of alpha from here comes out to be greater than 0.1, you should not take this approximation. Our approximation becomes invalid, and in that case what you will do here is that you will have to solve quadratic equation, get the value of alpha, multiply with C, you get C alpha, take minus log, you will get pH. Right? We will take up one example here, one small numerical problem here. How to find pH of 10 to power minus 2 molar acetic acid solution. See now. If concentration of acetic acid is 10 to minus 2, we assume its degree of dissociation is alpha. 1 minus alpha. Now we get concentration of acetate ions as 10 to the power minus 2 alpha. This also we get 10 to the power minus 2 alpha. Equilibrium constant for dissociation of acetic acid, Ka, is 1.8 10 to the power minus 5. For simplicity, what we do here is we are assuming it to be 10 to the power minus 5. An approximation we are using here. Now, Ka for this will be equal to concentration of acetate ion, which is 10 to the power minus 2 alpha, into concentration of H plus ion, which is 10 to the minus 2 alpha, upon it will be 10 to the minus 2 into 1 minus alpha. Right? Gets cancelled. Now we take approximation, which is alpha is negligible as compared to 1. If I take this approximation, we get here alpha square equal to Ka by C, which is how much in this case? 10 to the power minus 2. We get alpha as equal to Ka, which is 10 to the minus 5, upon 10 to the power minus 2 under square root. You can check from here that value of alpha will come out less than 0.1. If it is less than 0.1, as we discussed, then we say our approximation to neglect alpha here is valid, and we simply multiply this value with C, we will get C alpha, this value here, take minus log, we get pH of 10 to the minus 2 molar acetic acid solution. But if you were given, suppose 10 to the power minus 5 molar acetic acid solution, in that case the things would have changed dramatically. This will become 10 to the power minus 5 alpha, this also becomes 10 to the power minus 5 alpha, and here this also will be 10 to the power minus 5 alpha. Up to here everything looks okay only, that gets cancelled also. But see the case now. If now you try to neglect alpha as compared to 1, like we could do previously, see here carefully. In that case, what is going to happen? This becomes alpha value here becomes exactly equal to 1, which means that acetic acid is behaving like HCl, means it is behaving like a strong acid, 100% dissociation. Alpha, remember, is degree of dissociation, which tells us what amount of the acid or what percentage of the acid dissociates. If I am saying alpha is 1, it means 100% of the acetic acid is undergoing dissociation, and if that was the case, acetic acid would have been called as strong electrolyte, not weak electrolyte. Got it? So obviously this approximation is invalid. From here we can check comfortably whether our approximation is valid or not. Checking the approximation which you have taken is highly important. Sometimes if you take a invalid approximation just to save some time of calculations, your whole hard work may be ruined. Right? Now, similar example we give here for pH of weak bases. Very quickly we will go through it. We will discuss now pH of weak bases. One of the examples of moderately weak acid is ammonium hydroxide. There is no difference basically in finding the pH of weak acids or weak bases. Exactly what we did for weak acid, similar thing we are going to do for weak base also. So quickly we will go through it. See, NH4OH establishes an equilibrium to give ammonium ion and OH minus ions. If concentration we take as C and its degree of dissociation is taken as alpha, we get it as C alpha and C alpha. Now we got equilibrium constant for this weak base, and equilibrium constant for the weak base dissociation is known as Kb. So we got Kb for this, and Kb for this will be equal to concentration of ammonium ion into OH minus ion upon concentration of NH4OH. Right? Now substitute the values. This becomes equal to C alpha into C alpha upon C into 1 minus alpha. Again, same thing, exactly, so you can check now, gets cancelled. We get Kb as equal to C alpha square upon 1 minus alpha. Similar case exactly like we got for previously weak acid. We have got here quadratic equation. We try to simplify this. We take approximation of neglecting the alpha as compared to 1, and now we get alpha as equal to Kb by C under square root. Right? Exactly same thing you can understand now. If value of alpha comes out to be equal to or lesser than 0.1, we say our approximation to neglect alpha here is valid. Same thing we do, we multiply this C, we get C alpha, and minus log of C alpha is going to give you POH. Subtract from pKw minus POH will give you pH of this solution. This is how we get a pH of weak bases. Right, now one more type of questions are quite important here. To find pH of a mixture of acid and base, suppose we have got a mixture of two solutions, one of them is a strong acid, other one is strong base. How to find that? Suppose you are given a question that we have mixed 100 ml of 10 to power minus 2 molar NaOH solution with 200 ml of 10 to power minus 2 molar HCl solution. What will be pH of resultant solution? We have mixed these two. He is asking you pH of the resultant solution. How to do this? See, once you mix these two, this is a strong base, this is a strong acid. So obviously both are going to react immediately. Reactions are very fast, you know it. So we have NaOH plus HCl, and we get here NaCl plus H2. This is molar ratio. 1 mole of NaOH reacts with 1 mole of HCl to give 1 mole of NaCl, 1 mole of water. Right, now we are going to write number of moles or millimoles for the reactants. From that we find how many moles or millimoles of the products will be formed. NaCl, you know it very well, this is a neutral salt. So this will not have any effect on the pH. This is water obviously behaving as a solvent also. So again no effect on pH of the solution. Let us see now what happens. 100 ml of 10 to the power minus 2 molar NaOH we have got. So millimoles of NaOH we will have 100 into 10 to the power minus 2. Means it comes out to be 10 to the power 100 into 10 minus 2, right? So we get 1 millimole of NaOH. Come for HCl. This is nothing but, if you remember, molarity is given as equal to number of moles per liter of the solution, per liter volume of the solution. So number of moles, we get molarity into volume. If volume is in liters, we get moles. If volume is in milliliters, we'll get millimoles. So this is number of millimoles right now. Okay, now HCl, this is 200 into 10 to the power minus 2. Molarity into volume. In milliliters, we got millimoles, and this comes out to be 2. Now, 1 mole of NaOH reacts with 1 mole of HCl. So 1 mole of NaOH will react with 1 mole of HCl, and 1 mole of HCl will be left. 1 mole of HCl is left finally in the solution. 1 mole of HCl, oh sorry, this is millimole actually. So 1 millimole of HCl is finally left in the solution. 100% dissolution of HCl, like we have discussed previously. So we will get from there 1 millimole of H plus ion in the solution. Concentration of H plus ion in this solution will become, note one thing, that although initially HCl was present in 200 ml solution only, but you mixed it with 100 ml, so the total volume of the solution now is 300 cc. So this is 1 millimole divided by volume, which is 300, we get H plus ion concentration. 1 by 300 moles per liter. Right? Now take minus log of this H plus ion concentration, and this will be equal to pH of the resultant solution. Substitute this value here, the answer comes. Got it? So this is how we find pH for a mixture of one strong acid and strong base. Next category we have pH of dibasic acid, dibasic weak acid. One of the examples for this is H2CO3, carbonic acid. Now see, this is a dibasic acid, which means it can dissociate 2 times. Basically, it will produce 2 H plus ions. One more of this produces 2 H plus ions. That is why it is called dibasic. 100% dissociation is not possible. That's why called dibasic weak acid. Now, H2CO3, once it dissociates first to give H plus and HCO3 minus ions. Right? We assume concentration of H2CO3 given to you is C. The question is find the pH of a H2CO3 solution whose concentration is C moles per liter. Suppose the concentration of H2CO3 solution is C moles per liter and its first degree of dissociation is alpha. So we put here C into 1 minus alpha. Now concentration of H plus coming from first dissociation will be C alpha and bicarbonate ion will be C alpha. Now HCO3 minus can behave actually both as a acid as well as base. Here, because H2CO3 is a stronger acid as compared to HCO3 minus, it again goes dissociation, although the degree of dissociation is very less, but we show it again goes dissociation HCO3 minus and gives here H plus and CO3 2 minus ions. Now concentration of bicarbonate ion in this solution will be C alpha. Right? We assume degree of dissociation of bicarbonate ion is alpha dash. So it becomes C alpha into 1 minus alpha dash. Now we get it as C alpha alpha dash. Carbonate ion also will be C alpha alpha dash. Right? Now we are going to apply the equilibrium constants for first equilibrium and second equilibrium. See it carefully. Equilibrium constant for this is Ka1, first dissociation constant of the acid, which will be equal to concentration of H plus into bicarbonate ion, which is H plus into HCO3 minus upon concentration of H2CO3. Right? Ka1 for this will be equal to concentration of H plus into HCO3 minus upon H2CO3. We substitute the values and this becomes equal to C alpha into C alpha into 1 minus alpha dash. Remember this thing here, that final concentration of bicarbonate ion here is not C alpha. Why? Because already C alpha dash or C alpha alpha dash had dissociated again here. Got it? So final concentration of bicarbonate will not be C alpha here, it will be C alpha into 1 minus alpha dash. If you want, we can put it in large bracket also, like this. This becomes the case here, right? Upon concentration of H2CO3, which is C into 1 minus alpha. Got it? Now, second equilibrium constant will be Ka2, and Ka2 for this will be equal to concentration of H plus ions. Now see again. Remember one thing, that in equilibrium constants expressions we always put total concentrations. So concentration of H plus ion here will be sum of H plus coming from the first dissociation plus concentration of H plus coming from second dissociation. Means it will be C alpha plus C alpha alpha dash. Got it now? Now this is concentration H plus ions into concentration of carbonate ion, which will be C alpha alpha dash upon concentration of bicarbonate ion, which will be C alpha into 1 minus alpha dash. One thing more you people should have understood by now, that even here in the first equilibrium, we will have to put total H plus ion concentration, which is how much? Which is C alpha plus C alpha alpha dash. Quite a complicated formula it has become. Now, see carefully. If you see these two equations, Ka1 and Ka2 equilibrium here, we have got only two unknowns here. Although the equation looks very much complicated, but if you see carefully, we have got only two equilibrium, two unknowns. One of them is alpha, other one is alpha dash. Two equations, two variables. If we solve it properly, then we will get alpha and alpha dash. Now, pH of the solution will be minus log of total H plus ion concentration, which will be H plus ion concentration coming from first dissociation, which is C alpha, plus H plus ion concentration coming from second dissociation, which is C alpha alpha dash. Right? See, I'll tell you how to take approximations here. That also we'll discuss. Otherwise, this becomes very much fearsome actually. Now, we put equal to minus log. We take C alpha as common. We get here 1 plus alpha dash. Now, one small suggestion here. Usually, you can say 95-99% cases, the second dissociation is negligible. The weak dibasic acids, the second dissociation for them is negligible. Very, very less dissociation is there. So, what happens in those cases? Usually, in most of the cases, the second dissociation means alpha dash will be negligible as compared to 1. If we neglect it, see directly here, alpha dash if we neglect as compared to 1, we get pH as equal to minus log of what? C alpha. Right? So, there is actually no need to calculate alpha dash, but until unless you calculate alpha dash, it becomes difficult to calculate alpha. Now, we get minus log of C alpha. Simply this value will give you pH of this solution. We take some approximations here also to simplify. How? See that part. First approximation, alpha dash is negligible as compared to 1. Right? Even if this one we substitute, we take common C alpha, then it becomes C alpha into 1 plus alpha dash. Again, this is negligible here. Right? This one here take, this is C into 1 minus alpha, alpha we are not neglecting right now. This one alpha dash again negligible. Right up now? Clear. This one again we take as common C alpha and it becomes 1 plus alpha dash. Again it becomes 1 plus alpha dash, which again will be negligible here. If you see carefully, then Ka1 is nothing but equal to C alpha, because alpha dash has been neglected, into C alpha again because alpha dash has been neglected, upon C into 1 minus alpha. If you remember, this is exactly similar to acetic acid dissociation. We cancel C here and we get Ka1 equal to C alpha square upon 1 minus alpha. Right? Again, I take approximation here that alpha is negligible. If alpha is negligible here as compared to 1, we get the equation. If we neglect alpha here, then again the equation becomes that alpha equal to Ka1 by C under square root. Right? Exactly same thing. If the value of alpha is coming out here less than 0.1, happily ignore that. This alpha here, you get the value of alpha here. Multiply this alpha with C, you get C alpha, which is first H plus ion concentration, take minus log of this, you get pH. Because anyhow, the second dissociation is not going to yield any significant number of H plus ions. Right? Now, come here. If you see here, this was C alpha Ka2. C alpha, alpha dash has been neglected. Into C alpha alpha dash, again upon C alpha, 1 minus alpha dash again neglected. Very simple thing. This gets cancelled. And you get Ka2 as equal to C alpha alpha dash. If you pay attention here, what is C alpha alpha dash? This is carbonate ion concentration. Means certain times they ask in competitive exams questions like this also, that what is concentration of carbonate ion in a this much molar H2CO3 solution. One of the simplest way of answering this, that concentration of the carbonate ion will be equal to Ka2. Directly it can be answered in most of the cases, until as they change the concentration drastically, very high or very low. Moderate concentrations, you can simply put it C alpha alpha dash equal to Ka2. Right? So here we can give that concentration of carbonate ion will be equal to Ka2. Very simple way of answering this question.